Hey guys, our project is security programmable metamaterial antenna arrays for physical layer security.
My name is Dylan Turner.
And I'm Prachi Patel.
So, with the advent of the Internet of Things revolution, there's an increasing need to develop low-cost security protocols for our devices. Traditional security is done on software using techniques like encryption and can be expensive in terms of energy. So, any possible reduction in this energy cost has potential to propagate savings to the tens of billions of IoT devices. So our project is about investigating a computationally simpler security protocol for our devices to talk to each other. So what is the solution? It's not very obvious based on just the title of our project. So I'm going to break this down a little bit. Physical layer security. Unlike the software security, like I previously mentioned, physical layer security is about exploiting physical properties of a system. So our project in particular focuses on directional modulation, which is a technique used to preserve a signal in one direction and scramble it in every other direction. Like in this image up here, this is our antenna, and this guy is receiving a good signal, and the guy on the left is receiving a scrambled signal. So how do we achieve directional modulation? It's using metamaterial antenna arrays. A metamaterial is any man-made material that is designed to exhibit some special property that's not usually found in nature. For example, in our project, we have metamaterial antennas, and these are designed so that when a signal passes through it, it is phase shifted by a certain amount. Now, a phase shift can just be thought of as a delay in your signal, and this delay is controlled by the voltage applied to the element. So our project has 9 of these metamaterial antennas strung together to form an array. And using this array, we can program it to secure our transmission. The way we program it is with these codes that you see on the bottom right here. These dictate the voltage that's applied to each element. So in this example, red means that the first element is going to have a voltage applied to it, and then the second element will not have a voltage applied to it. And as the signal goes through each of these elements individually, the combined effect is that our signal will be shaped into a directional beam. Okay, so I hope that explains the title a little bit more. Essentially, we have an array of antennas that are made of a special material called the metamaterial, and we're using that to secure our devices on the physical layer. So this whole directional modulation scheme has been done before and shown to work at low data rates. However, there's a problem. We want to send data quicker or at a faster rate. So when we do this, we need a wider bandwidth. And bandwidth is just the range of frequencies that you're using to transmit your signal. A good analogy for this is how when you're sending water quicker through a hose, the stream becomes wider. So this is normally fine, but it turns out that the properties of our antenna are frequency dependent, meaning the parts of our signal that are far apart in frequency will be affected differently, and that's going to result in errors. So the solution to this is called symbol precoding. And there's a lot of math on the right side of the screen that goes into it, but I'm not going to bore you with that. Essentially, as our signal comes through, it's multiplied by a precoded vector, which has been specifically calculated to negate the frequency-dependent effects of our antenna. So investigating symbol precoding and implementing it into our system has been the main focus of our research this summer.
GNU Radio. We use GNU Radio to implement our work. GNU Radio is a software that allows us to create signal processing systems. In GNU Radio, there are these flow graphs and these blocks that we put together, and these are pre-made, but we can also create custom-made blocks. Our job is to implement symbol precoding. Here is a snippet of our code that we use in order to implement that. We have spent half of our internship working on this, and the reason why we use GNU Radio is because the radio creates a signal that we transmit into the antenna. So now that we've talked about GNU Radio, let's talk about testing. When it comes to testing our system after we implemented symbol precoding, we have to test it in 3 different phases. The first phase is simulation. In simulation, we test our system in software to make sure that everything is working properly. After that, we move on to basic equipment. In basic equipment, we use the USRP B205 minis. Here is the USRPs that we're using. We use these specific USRPs because we need them to use for the 3rd phase, which is where we test the metamaterial antenna array. In this is a custom-made prototype that we have used, and we can't just move straight to the third phase because there's just many unknown variables because of it. And we'll be testing the antenna in bush at the anechoic chamber. Now that we've talked about our 3 different phases, let's look deeper into the basic equipment testing. In basic equipment testing, we are testing the USRPs using 2 different things. First, we're using a wired connection to make sure that everything is working. This keeps the signal intact by using a wire. After that, we move into the antenna. In this, it's more tricky because there's just more variables, but luckily everything worked over here. Lastly, our 3rd phase of testing is the anechoic chamber. In the anechoic chamber, it's a room that absorbs the signals that hit against the wall. The walls are padded with foam, and here is the horn antenna over there and the metamaterial antenna. The horn antenna acts as a receiver, and the metamaterial antenna is our custom prototype, which also acts like the transmitter. When we're looking into the anechoic chamber, we go onto our computer and create the flow graphs. Using those flow graphs are connected to the USRPs, and the USRPs are fed into the metamaterial antenna. Once we were done with that, it's time to look at the results. In this thing, we've tested our system in 3 different angles. One was 0 degrees, the next was 135 degrees, and 75 degrees. So when we tested it during the 0 degrees and the 135 degrees, our signal was scrambled, so we didn't receive any packets. After that, we moved on and tested it into the 75 degrees, which is the correct angle, and we received some packets. This shows that symbol precoding works as a proof of concept. So for our future work, our short-term goals are to automate measurements. So when we were testing our system in the anechoic chamber, like me and Dylan were just yelling at each other like, hey, stop, start. And that takes variability in time. So like not everything starts at the same time. So that's one of our goals. Next, we need to determine power restrictions to protect the hardware. So in this, we can only do 5 dBm, which is like half of a milliwatt. So this can burn our reactors if we go more than what we need to, but yeah. And then for long term, we're trying to refine our system so we receive all the packets, and we're trying to incorporate additional layer of security. And in this aspect, we account for distance. So as you can see in this picture, there's an antenna, and both of the people are in the correct angle. So like everyone can hear what like is trying to be transmitted to that one person. So in order to do it, we're trying to add extra security so only the right person can hear whatever needs to be heard.
Thank you, guys. Any questions? Yeah. That is a great question. We have more details on our poster down there. The answer is we got quite a low amount of them. And we were struggling a lot with that, but we are very happy with this in the end because it really could not have happened by accident. So this is a proof of concept showing that simple precoding works. So we're pretty happy with that. But of course, in the future, if we had more time, there's a lot of things we could do to isolate where that problem is coming from. Mhm. We never really measured the rate because the way we had implemented it was using GNU Radio, the scripts that we wrote for precoding, when we put them on there, they became super slow. Like we actually had to split our processing into online and offline. So we prepared our information just before we transmitted it, then we would send it over and then process it afterwards. So it was super slow, but as a prototype, that makes sense. In the real world, it would be much quicker, but we don't have those measurements. I assume once it's all working, it would be similar rates to what we currently have. Yeah. That goes a little far down into the math. So if you want, I could explain that to you at the poster. But interestingly, normal antennas usually have about like up to 4,000 elements. So that's one feature of this that makes it a much cheaper solution. Thank you.